Do. Hello, everyone, and welcome to our presentation for today. I am going to share my screen with you all so you can see what we're up to on today's broadcast. And the session that we're hosting today is fan troubleshooting and system effects. Our speaker today is Dave Maletich from New York Blower. And as you know, if you've attended any previous sessions, I am Lisa Cherney, the Education Manager from AMCA International, and I'll be moderating today's program. So we're very glad to have everybody with us today. The general guidelines. Everyone is muted for the session. If you have any questions, you can submit them at any time during the program. There's a little bit of a correction on here. Dave is going to intersperse Q&A throughout the program, so you don't necessarily have to wait until the end to get your questions answered. We are recording the session, and both the recording and the PDF version of today's slide deck will be posted on the Odell website within 48 hours. And as usual, if you are seeking PDH credit for today's broadcast, please remember to stay logged on for the entire program and fill out the survey that will be emailed to you 1 hour after today's program. So again, the Q&A option is where you will submit any questions. Don't forget to click send. I do remind you that everyone in the audience can see the questions that get posted. And if you do have a question that's a little too involved to put in writing, or it's a multi-topic question, please go ahead and use the raised hand feature on your control panel at the bottom of your screen, and we will verbally let you ask your question. And as I said, Dave is going to intersperse Q&A throughout the program. For PDH credit today, AMCA International has met the standards and requirements of RCEP. Credit will be reported to rcep.net, and you will receive a certificate of completion within 30 days of today's program at the email that you use for registration. As such, RCEP does not endorse any content that is in today's program. A quick disclaimer that the webinar today is provided by AMCA as an educational service only. It is not intended to serve as professional engineering or manufacturing advice. The views and opinions expressed are those of the presenter alone. And in making this activity available, AMCA is not endorsing, sponsoring, or recommending any particular company, product, or application. And also, under no circumstances, including negligence, shall AMCA be liable for any damages arising out of anyone's reliance upon or use of the content contained today. The program is copyrighted. If you feel like reproducing, distributing, displaying, or using the materials, please just ask us for permission in writing ahead of time. And now the most important part is our speaker for today. Dave Maletich is Vice President of Marketing for the New York Blower Company. He is a colleague of Mike Heumann, who presented last week. Dave has over 30 years experience in the fan industry. He is a current ASME Nuclear Air and Gas Treatment CONGAT committee member. He's also a member of multiple AMCA committees and very dedicated to AMCA's mission. He presents fan-related seminars, not just for AMCA, but for ASHRAE, OSHA, ACGIH, a bunch of universities and engineering firms, and he has an unbelievable wealth of knowledge about system effect. So with that, I am going to stop sharing my screen and turn the presentation over to Dave. Thanks for joining us, Dave.
Uh, Thank you very much, Lisa, for the kind introduction. That was very nice. Hopefully everybody can see my screen. Are we good? Assuming that's a yes. So let's talk a little bit about our objectives. What are we going to talk about today? We're going to talk about how fans are tested and rated in accordance with AMCA Standards 210. That's how they're tested. AMCA Standard 211. That's how they're rated. Talk a little bit about how ductwork configurations mounted near the fan can change the way a fan performs. And finally, we're going to talk a little bit about how in situ fan installations can differ in fan performance from the catalog performances and what this might mean. So obviously, as Lisa mentioned, presentation is broken down to segments. Any questions that come up, throw them out there. I'd like to sit there and handle them when they're relevant and at the time that we're going through them. But if you don't want to sit there and do it at the end, you can do it at the end as well. As Lisa sent out, there's going to be a quiz. At the end of the presentation, we're going to go through a series of videos. And in that video, most of the videos, in fact, all of them except one, shows a system effect or how a system changes the fan's performance. However, one effect is an actual system effect in which it changes the system's performance, not the fan's performance. So it'll change its point of operation on the fan curve. Everybody who gets the correct answer will receive a gift prize at the end. So let us know, and we'll definitely send that out. Here we have a fan in an AMCA accredited lab, and this is how all fans are pretty much tested in accordance with AMCA standards. This is a figure 12 configuration. We have a fan with an open inlet. That open inlet has a inlet bell on it that uniformly loads the wheel and minimizes entry losses into the fan. Discharge side of the fan, we have a straight run of ductwork. That straight run ductwork allows for the velocity profile of the air as it discharges the fan to even out before it enters into the bulkhead and into the test chamber. On the drive side of the fan, fan's being driven by a motor through a VFD. A lot of times people think, hey, I'm just going to get the amp readings and everything off the motor VFD package. Problem with that is that those items are not calibrated. Typically, it's very difficult to calibrate a motor VFD at all the different load ratings that the motor VFD package might see. So consequently, most fan manufacturers are going to use some load cell device, such as a torque meter, to record energy consumption of the fan. This is pretty important in that, notice there's no V-belt drives on this. So if you have V-belt drive losses, those V-belt drive losses are not included typically in the fan's performance. So if you have a fan that's running at, let's say, 48 brake horsepower, it's really good to sit there and go to some chart table for a belt drive system and identify what those losses might be rather than just using that horsepower. Because if you're running on a VFD, there is no service factor on the motor, or if you're running at altitude, there may not be a service factor on the motor. And in those cases, that motor might be overamped and might burn out prematurely. You might shorten the life of it. Behind the bulkhead is a test chamber, and inside the test chamber is a series of nozzles. By opening and closing these nozzles, we can correlate or change the characteristics of the chamber to match the fan's performance. So if it's a high flow fan, you're going to have more open nozzles. If it's a low flow fan, you're going to have more closed nozzles. Any questions regarding how fans are typically tested and rated at this point? Okay, we'll move on to the next session, is how are fan curves generated? You probably saw this in Bill's presentation a little bit earlier, Bill Howard, in that when you look at a fan curve, pressure, usually red on the left-hand axis, flow is usually red on the bottom, energy consumption is typically on the right-hand axis. And when we first test a fan, we close off all the nozzles, pressurize the chamber, record the energy or the work that the fan's doing. In this case, the little square dot here is energy consumption. The round dot here is static pressure versus flow. And the fan's producing about 6 inches of static pressure, consuming about 6 brake horsepower. And we just simply open up the nozzles until we have enough points to create a fan curve. And in this case, we've only used 4 points to create a curve. More points you use, the more accurate the curve is. Most fan manufacturers are typically between 8 to 12 points in order to generate a fan curve. A lot of times people come to us and say, hey, I got a fan curve here. Where is my system going to operate on this fan curve? From a fan manufacturer's point of view, the fan can operate at any point along that curve. There's nothing that's going to govern where the fan's going to operate except the system. So when a customer comes to us and says, hey, I need 10,000 CFM and I'm going to generate 5 inches of resistance, what they're really saying is that they have a point out of many points that forms a system curve. And that system curve has an infinite number of points on it. And it's just simple to go back again to Bill Howarth when he did the fan laws. Second fan law was pressure varies by the square of the change in flow. In this case, the system operates very similar in that pressure varies by the square of the change in flow. And within a given system, what I mean by given system, we don't add branches, filters don't get clogged, we don't open up registers. Within a system, if you increase flow, pressure goes up, decrease flow, pressure goes down. And then the fan, where the fan's going to operate is the intersection between the system curve and the fan curve, in that point only. If you open up a register, this system curve is going to shift to the left, to the right, this direction here. If you close a register or filters get dirty, close off a branch, the system curve is going to shift up the fan curve. When you do those things, you'll notice it changes the system curve, but it does not change the fan curve. And, you have one question. Is static pressure on the chart the fan static pressure or the static pressure at the outlet? That's a very good question. And thanks for asking that. Generally, when we have fan performances, it's always at the fan's inlet conditions. So when we see a temperature, pressure, flow, actually, let me rephrase it. When we see temperature and other conditions, we always put that at the fan inlet. But fans, when you see static pressure, that is static pressure at the inlet and outlet combined. So if you see 10 inches of pressure for the fan, that could be 5 inches of inlet pressure, negative at the inlet, 5 inches positive at the outlet. Or it could be -2 at the inlet, +8 at the outlet, or some variation that adds up to 10 inches of pressure. So it's kind of a combined measurement there. Does that answer your question, Pat? Okay. All right, so moving on. Any other questions regarding generating curves where fans are going to operate on the fan curve? All right, let's talk a little bit about testing and rating of fans. Fans are tested in accordance with AMCA Standard 210. AMCA, meaning the Air Movement and Control Association, pretty much governs how fans are, the methodology for testing and rating a fan. So when you're looking at how brand A and how brand Z were tested, if they're AMCA certified products, you can be pretty much assured that the same testing methodology was used for both products. Fans are rated in accordance with AMCA Standard 211, and that's how we catalog the performances. Basically, what that means is that we take that curve that was tested in accordance with AMCA Standard 210, and we rate it roughly plus or minus 2.5 to 3% flow pressure, 5% on energy consumption, and that's what is allowed to put in our catalogs. So when we have an AMCA product, certified product that we manufacture or design, we'll build a product, design it, test it, and then we'll send the catalog data that we just created along with our fan to AMCA, which would be a third-party validation organization. They would retest our fan, and they have to be able to duplicate our catalog performance, plus or minus 2.5, 3% flow pressure, 5% on energy consumption, in order for it to be an AMCA certified product. If they can't do it, we cannot put this label on the fan and it will not be AMCA certified. unless we resubmit new data to them or we decide to use AMCA's data itself as a third-party validation organization. So over the life of a fan, fans can be manufactured for 10 years, 15 years. What's to assure that during that lifespan of the manufacturing process that that fan maintains its ability to perform as catalog? After all, fans are fabricated, you got different people putting them together, you have different fixturing devices, those can get worn out, they can go out of tolerance, etc. Every 3 years, AMCA requires that each fan line that's AMCA certified be submitted for a check test. So after 3 years, they'll give us a call or send us a letter saying, send me this size fan and we need to check test it. So, and it could be any size, it could be a 22, it could be a 27, it could be a 40-inch fan. They'll pick a size, we have to build it, submit it to AMCA, and they have to be able to replicate our catalog data, again, plus or minus 2.5% flow pressure, 5% energy consumption. If we can't do that, or they can't do it, we potentially lose our validation for that product line. So that's what ensures that over the life of a fan, that it still performs, even though we're still fixturing it and those things might go out of tolerance, that they're going to perform this catalog. So it's a really good methodology to pair brand A to brand Z, and making sure that what you're getting is something that's going to perform equally and is directly comparable. Any questions regarding the AMCA certification process or what AMCA certification means? Okay, moving on. So sometimes fans do not perform as cataloged. What causes that? Well, we have to look at how a fan is actually getting tested. Fan this is a centrifugal fan, this is an axial fan or an inline fan. Notice that both of them have bell mouth inlets to them, allows for uniformly loading the wheel, top, bottom, side to side, eliminates entry losses into the fan. And in both cases, we have a straight run of ductwork to allow for that velocity profile to even out before it enters the bulkhead. If your duct configuration varies from that, it may or may not affect how the fan performs. So for example, on the discharge side of the fan, we always have to remember air has mass and wants to hug the outside of a volute shape or the outside of a housing. So when the air discharges from the fan, it's not uniform. So most of the air on a centrifugal fan discharges at the top part of the housing or the ductwork, bottom portion right behind the cutoff sheet. There can actually be a little bit of a negative pressure region. And it takes 100% of effective duct length for that velocity profile to even out. What's 100% of your effective duct length? 2.5 duct diameters for the first 2,500 feet of velocity, an additional duct diameter for each 1,000 feet of velocity after that. So if you have 6,000 feet of velocity, you should have 6 duct diameters. If you have 1,000 feet of velocity, you still need to have that minimum 2.5 duct diameters. That is to get full regain. However, if you look at this chart here, or this picture, at 50% of your effective duct length, you're getting about 80% of your regain there. And that's a pretty significant amount. And what's important about this is if you have something in the, like a wall or something out there that prevents you from having your 100% of effective duct length, better have something than nothing. So just don't give up on it. If you can get 50% of your effective duct length, you're going to get 80% of your regain back. That's a very significant improvement. The remainder of this area from 50 to 100 is what I typically call a polishing area. You get an improvement, but it's not as significant of an improvement as that first 50%. Now, if you have to have an elbow, it's much better to have this position A elbow at the bottom here than a position C elbow. Again, air hugs the outside of the volute shape, comes up here, and if you have that position A elbow, it continues along the outside of the elbow, and then you can put your straight run duct here and get your regain at this point. If you have a position C elbow, air hugs the outside of the volute shape, hits the back of the elbow, has to get reaccelerated out of this duct, and you're going to have a fairly significant loss there. A lot of times system effects are a result of issues that are out in the field. So they put this 90-degree elbow here. They're getting noise complaints from the neighbors over in this area here. Put a position C elbow on the discharge of the fan so air comes out. Deadheads up against the top, has to get reaccelerated out this direction. Fairly significant losses at this point. Inlet side, we have this abrupt 90-degree elbow. Creates a lot of turbulent flow as air enters the fan. This is the actual size of the inlet. They had to put this orifice plate here on the fan to gooseneck it down from this size down to the ductwork size. So when this fan was tested in the field, it was only performing about 60% of its catalog rated flow. I have no idea. This is on top of a federal building. I have no idea why they designed it this way. Top horizontal fan, position C elbow. Air deadheads here, has to get reaccelerated back out. This rain cap on the top, deadheads the air again, has to be bent 180 degrees down. If this was an upblast fan, that would have been a significant improvement right there. And then if they put a no loss rain hood on top of that unit, that would further increase performance because we wouldn't have any losses associated with this appurtenance here. Low combustion air system, high pressure fans. Again, you have these elbows, position C elbows. Air wants to go around here, deadheads against the back, has to get reaccelerated out. They have these wafer dampers, which are vertical. Nice thing, a lot of times people think guide vanes improve flow. Guide vanes can actually hurt flow as well if they're improperly located. So this damper going vertical means that the air is going to come in at this high velocity. It's going to enter the one side of the damper. So you're going to have a high velocity side of the damper and a low velocity side of the damper. And that's going to extend the non-uniform profile of air discharging this damper system much higher than if they were to put the damper higher up in the system or right at the discharge of the fan. Here we have a fan that's exhausting fumes from a lab, top of a portable lab structure. They have isolators. Isolators are nice because they prevent the vibration of the fan, sound of the fan from being transmitted back into the building. However, there's no flex connector here. So the fan is functionally pipe bound to the ductwork. So while noise isn't being transmitted here, it's being transmitted through this duct back into the building to the hood. And so consequently, they're not really saving anything by putting the fan on isolators. Also, what you're going to see in the video presentation a little bit later, the aspect ratio of this inlet box is very poor, which shoots the air too high into this duct here. So we're only using the top portion of the wheel to move the air. The bottom portion of the air here, or the wheel here, doesn't see any air. So we're only going to use a portion of the wheel to move the air. Fan's going to underperform. Finally, we have no ductwork on the outlet, so we're not going to get any static pressure regain at that point of operation. Here's another modification. This fan here was moving lavatory or bathroom exhaust air out of the building. This is the clean air intake into the building just behind it. When employees were complaining about the smells getting back into the building, their engineering staff developed this little duct system to redirect the smells away from the clean air intake. However, they're going to have to speed up the fan because there's additional losses associated. You got this 90-degree elbow here, abrupt two-bore elbow here, and then 180-degree elbow at this point. You're going to have some system losses unless you speed up the fan. You're not going to be pulling stuff out of the lavatories like it originally was designed to do. Oftentimes, you've probably seen people have a boneyard of fans in the back, big facilities, or they buy stuff on an auction. This is sometimes what happens. Here we have an upblast fan. Customer used 50-gallon drum container as a duct system to redirect the air out of the fan, kind of an abrupt position C elbow, and direct it into this cyclone in order to clean the air. As you'll see a little bit later, if they could have bought a fan that was top horizontal that blew directly into the cyclone, they would be saving, while it would have cost them more to buy that fan, they would be saving money in the operation of the unit over the lifetime, and their payback would have been relatively short. This is not actually a system effect, but this is kind of remind us that three-phase motors can be wired. You have a 50-50 shot that you're going to wire a motor either clockwise or counterclockwise in its rotation. In this case, this is a dust handling system. Customer felt at the end outlet of the fan, air was being moved, so they assumed that it was rotating the wheel in the correct rotation. However, the rotation was backwards. And it was still fast enough in order to capture the dust. However, it wasn't fast enough to convey the dust in the system. So the dust dropped out in the ductwork, dropped out in the fan. Unless their load calcs are way overdone for supporting their ductwork, it's a pretty unsafe situation in which you have overloaded duct with a lot of dust inside of it that could collapse and cause some injuries on the shop floor. This is actually a good system. In this case, we have a fan exhausting from a factory. We have a silencer at the inlet of the fan. Silencer does two things. One, acts as a straight piece of duct, so we don't have any turbulence going into the fan. Secondly, it minimizes the transmission of noise from the fan back into the building. Discharge, we have a rectangular round transition, round piece of duct, and we have a no-loss rain hood here. No losses associated with air movement through the duct. However, when the fan's off, rain comes down. Rain never comes at a straight vertical. It always comes at an angle, hits the side, and drops out on the outside of this duct here. Any questions regarding system effects before we go to our presentation? Okay, we'll move on. Following demo was done in 2020 for the AHR show in Orlando. And functionally what it does is it shows a variety of different duct configurations and how those duct configurations can change or alter the way a fan performs. So this opens up to what our poll question is. All the system effects that are shown in the demo directly affect or change how a fan performs. And what we mean by that is each one of them is going to change the shape of the fan curve. However, there's one system, except for one, and there's one system effect that doesn't affect the fan curve, but does change the system curve. So anyone who can pick that one out will win a prize, and we'll talk about that at the end. So we're here, Lisa. Do you want me to leave control of this, or do you want to, how do you want to handle this?
You are good to keep control, and I will run the videos from my end.
Okay, so go ahead and run the 90-degree elbow.
Okay, I lied. You need to stop sharing your screen, please, Dave.
Okay.
Thank you.
Hello, my name is David Maletich. I'm with the New York Blower Company. I'm Vice President of Marketing, and today we're going to look at system effects, or how inlet and outlet discharge configurations change fan performance. And you'll see by adding different inlet configurations, it'll have a direct effect or change in the fan's operating performance. Before we get started, let me just explain a little bit about how this fan is configured. First, the fan has an open inlet that allows the air to uniformly load the wheel, and we have a straight run of ductwork just as the fan gets tested at AMCA to allow for the static pressure to regain before it goes out to atmosphere. So the first thing we're going to do is we're going to grab a piece of ductwork. It's a 90-degree elbow, and you can see there's no vanes inside the elbow, and we're going to see how it affects the fan's performance. So we put it on the fan's inlet, and looking at the Magnehelic gauge over there, you can see that the fan performance has gone down significantly just by putting a 90-degree elbow on the inlet of the fan. What's happening is air has mass, and when anything has a mass to it, it wants to go in a straight line. So the air enters this duct uniformly, it wants to go straight down to the bottom, and then it has to bend 90 degrees into the fan. So basically what we're doing is we're loading the bottom half of the fan wheel as it's rotating, but the top half of the fan wheel doesn't get any air, so we're not fully utilizing the mechanical aspects of this fan. Now the next thing we're going to do is we're going to add an elbow, take off this one here, and we're going to add an elbow that has a turning vane in it. And that turning vane basically splits the duct into two sections. So when we put it on here, look at the Magna Helic, you'll notice that there is still a loss associated. However, that loss is much less than what it would be if we had an elbow with no vanes in it. So again, air comes in, loads this uniformly. However, instead of the air going to the bottom, this vane forces the air to turn in two sections. So now we're better utilizing the mechanical aspects of the wheel as it's rotating.
And Dave, we have a question that has come through the Q&A. Tim is asking, one of the slides mentioned 2.5 duct diameter at the fan discharge is preferred. Is there a similar rule of thumb for the fan inlet?
That is a really good question and a really difficult one to answer. You'll see in the corkscrew portion of the videos that my experience is inlet ductwork considerations are way more subjective than discharge. Discharge is relatively easy, and those rules are pretty solid rules to follow. But on the inlet side, turbulent air, especially circulating air, stuff that's coming off of a cyclone or some device that creates a spin, I've seen go 300 feet down a piece of duct and just never stop. And that's because you have two vortex creating devices, you have whatever's creating it, and you also have the wheel. The fan wheel is rotating, so if it's rotating clockwise, even without any kind of pre-spin device, it's starting to spin the air in a clockwise position. If it's counterclockwise, it's going to rotate it in the opposite direction. And so consequently, you sometimes need to have mechanical devices in the gas stream on the inlet side to forcibly correct the situation. Also, because the fan's sucking air, those system effects can get elongated and take a much longer distance to correct. So those rule of thumbs are really for the discharge side. They don't really necessarily work on the inlet side. And you just have to look at the situation, what you have, and try to make corrections based on your experiences. And if you don't have, you feel a little bit uncomfortable, there's a lot of people out there that have some experience with that, and contact either somebody at AMCA or, like, throwing this out there, Phil Howarth, who did a presentation earlier, has a lot of field experience and is very good at doing these corrective measures as well. So hopefully, Tim, that answers your question. If it doesn't, throw something else up there as we're going through the next demo.
Okay, and we will move on to the next video. Dave, any introductory comments about corkscrews?
No, we'll see what the what it shows, and then we can talk a little bit about it afterwards.
Okay.
Fans where you have a wall here, and so you don't have a whole lot of space in order to run ductwork into the fan. And what we're going to do is create a corkscrew and see how corkscrews affect the fan's performance. So put a 90-degree elbow on the inlet of the fan, and we're going to sit there and put it on in this direction here. Now basically, when you're looking at this, you have to also listen to it audibly because what you're going to hear is either the vibration and the fan noise go up or down. Now in this case, air is coming in this direction. It wants to go into the corkscrew, so it's starting to pre-spin as it goes through the fan. Pre-spinning of the air means that the wheel or the air is going in the same direction that the wheel is rotating, and the air cannot get moved as efficiently as what it would be if it was coming in straight and laminar. And that results in a fan that's quieter, but also when you look at the Magna-Helic gauge, you'll notice that the static pressure generated by the fan went down pretty significantly. Now when I turn this 180 degrees, you'll notice that, like I said, kind of listen to what's happening, is that I put it on here, the fan gets much noisier, sounds a little bit rougher, and also the Magna-Helix is showing the pressure went up as the fan's operating. So that extra noise is basically, we're now counter-spinning the air as it enters the fan. Air is going in the opposite direction of the wheel rotation, kind of like how when you're, if you're rolling down the driveway backwards, put your car into gear, push it forward, it effectively moves, but it does it in a very rough manner. Same thing happens with the air as it enters and discharges the fan. So if we were actually able to take an amp reading and do an efficiency calc, even though this fan's producing more pressure, it's doing it much less efficiently. Horsepower has actually gone up, and that's kind of evident in the amount of noise that the fan's producing.
Any questions on corkscrews? I should mention one thing with turning vanes is that when you have a turning vane, if the air is entering the turning vane unevenly, it's going to exit the turning vane unevenly as well. So it only works when uniform air is going through it. It doesn't work very well when non-uniform air is going through it. So, okay. Lisa, you want to go to the next video?
Is an inlet box. Here we have an inlet box, and as we saw in the presentation earlier, there's certain aspect ratios that you want to have with an inlet box. This one's a very poor aspect ratio. It's very short in this direction compared to its width, which is very long. It's a very rectangular inlet box. We'll put this on the fan and we'll see what happens. Okay. Notice that the fan's doing a couple different things. One is efficiency, or the amount of pressure that the fan's generating, went down significantly. It's almost half as much as what it was originally. Second thing you'll notice is that that needle is not very stable. It's going up and down. This inlet box has actually put the fan into a surge condition. And those surge conditions on a small fan are pretty bad in that, one, it creates a lot of noise. It goes up and down. And then secondly, what you'll notice is that if you have an application where you need smooth laminar flow going through it, like let's say a combustion air system, it's very hard to maintain a constant flame when the air is going up and down pretty consistently. The other thing that having a fan left to peak is when the fans get very large, like you have a 2, 3, or 1,000 horsepower fan, that vibration can become pretty significant and actually cause ductwork to crack. It can also cause foundations to crack. Now here we have an inlet box that's a little bit better designed. Its aspect ratio is much more square. Its depth compared to its width is much more on the square side of things. It's not an elongated rectangle. The other thing you'll notice is that we've added turning vanes to this inlet box. Turning vanes, just like with the 90-degree elbow, help efficiently load the air as it goes into the fan. Put this onto the inlet of the fan, and you'll notice that, yes, we do have a loss associated with the inlet box, but it's much less than the improperly designed inlet box losses.
Any questions regarding inlet boxes? One thing we should mention on inlet boxes or anything that you add a turning vane is if you have long stranding materials going through the gas stream, such as a paper trim system, or say you're working on, or fans working on a diaper manufacturing facility, that stuff can clog up on the turning vane and create blockages in the gas stream. Also, if there's any abrasives going through the gas stream, those can abrade away or eat away at turning vanes, causing potential metal failures that might go through the duct system and damage other pieces of equipment. Okay, Lisa, you want to move on to the next video?
And it's just a straight run of ductwork. You can see that it's just a long tube, and there's nothing inside of the tube, just a very hollow piece, and we're going to see what happens. Putting this on the fan, you'll notice that there's a loss associated with this straight run piece of ductwork, and that loss is actually relatively significant. Now, a lot of people think that that's associated with friction loss through this ductwork, the amount of effort that it takes to pull air over a piece of sheet metal or a piece of Schedule 40 pipe. Now, if we add this venturi to the inlet, just a plain venturi, see what happens. You'll notice that almost all the losses associated with the straight run of ductwork are gone, that there's virtually no losses. And what you soon realize is that those losses are associated with the entry loss over this sharp-edged orifice. And that entry loss is pretty significant, almost 1/10 of an inch. By putting this venturi on the inlet, you've eliminated almost all of those entry losses associated with that. And we can watch the MagnaHelic again.
Any questions regarding, it's actually a bell mouth, that's not a venturi inlet. Over the years, I got to have the same venturi, but any questions regarding bell mouth inlets? That also is effective if you put a flange there too. And if you go to ACGIH, they do talk about entry losses, either the sharp-edged orifice, a flanged inlet, or a bell mouth inlet. And those all going from sharp edge is the least efficient, flange is better efficiency, bell mouth is the best efficiency. So depending on your hood design and how you want air to enter into the duct, that will definitely affect how well the system performs. Lisa, next one.
And the problem with corkscrews is that corkscrews can go down a piece of ductwork for an extended period of time. The fan itself wants to create a venturi or a vortex as the wheel rotates, and if we create a vortex over here, that vortex will continue down that straight run of duct. And if you look at the MagnaHelic, you see that the losses were almost the same as the losses we saw in the first part of the video when we put the corkscrew right at the inlet of the fan. And that's because that air wants to pre-spin all the way down the duct, because the fan's creating a pre-spin, this corkscrew is creating a pre-spin, and there's no place for that pre-spin to go away down this ductwork. Now, the only way to eliminate that is to put perhaps a T or a cross section in the duct, known as a vortex breaker, to help break that vortex and prevent that pre-spin from continuing from here all the way into the inlet of the fan.
So Tim, hopefully that kind of demonstrates a little bit about that 2.5 duct diameters and how vortexed air, spinning air can travel through duct systems. And if you do have something like that, really recommend looking at AMTCA, I believe it's AMTCA standard 201, which has 2 different straightening devices that are very effective. If you don't follow those guidelines, you can oftentimes put something in there that you think is going to work, but ultimately doesn't work. So if you put a T in there and the T is, let's say, 1 or 2 duct diameters, it's not going to be long enough to break that vortex, and you're not going to have very much effect on correcting the system. So, Lisa, if we move on to the next video.
We can put on the fan's inlet. So we're going to disassemble the unit. We're going to move the readout device to the inlet of the fan, and we're going to see how changes in discharge configurations also changes the fan's operating performance. As you can see here, we've moved the measuring device, the pitot tube, to the inlet of the fan, and we're going to measure or examine how fan performance changes when we add or change the ductwork configuration on the discharge side of the fan. So the first thing we're going to do is we're going to add a straight run of ductwork to the fan. The straight run of ductwork allows for the velocity profile to even out as the air discharges the fan. And what I mean by velocity profile is when we take this piece of paper here, just a normal 8x11 piece of paper, put it at the discharge of the fan, notice that the air actually is negative pressure here and actually sucks the piece of paper into the fan. And if I put it on the other side of the volute shape, it's positive pressure and it actually blows the piece of paper upward. So as air discharges the fan, it's not laminar across the whole discharge, it's all focused on this section of the fan. Putting this ductwork on the outlet of the fan, notice that there's a change in performance when you look at the Magnehelic gauge, that it's actually dramatically improved. And the reason it's improved is that the air velocity profile has gone through this piece of ductwork has actually evened out. So if I look at it here, put the same piece of paper here, notice it blows the piece of paper up. It's no longer negative pressure at this section. And if I do the same thing at the other side, it's positive pressure as well. So now we have laminar flow, and that laminar flow results in increase in performance. Now when you have a straight run of ductwork, you want to have the proper length, which is typically 3 duct diameters for the first 3,000 feet in velocity and an additional duct diameter for each additional 1,000 feet in velocity. However, it's better to have something rather than nothing. So if you're space constrained, it's good to have a short piece of ductwork rather than no piece of ductwork. So if we take this rectangular to round transition, the same one that we used when we were doing the inlet measurements, put it on the outlet of the fan, and again, no turning devices inside of it. Put it on the outlet. Notice that there is again an increase in performance when we look at the Magnehelic gauge. And if I take the same piece of paper, notice that even in this short distance here, we've already started to get some evening out of the velocity profile. No longer is the pressure negative on this side. You can see it's blowing the piece of paper up. And it's starting to even out on this side. It's not as harsh as what it was as the air was discharging the fan.
Any questions on discharge side of the fan, having straight runs of ductwork and how it changes fan performance? Okay, Lisa, I think we can move on to, I believe, our final video on elbows at the fan discharge.
At the discharge of the fan. And if you have an elbow, like this 90 degree, there's a proper way to have the elbow orientated and there's an improper way. The improper way is to put it where it breaks the back of the air. The fan has a volute shape. Most of the air discharges on this side of the housing or the outside of the volute shape. And if we put an elbow that breaks the volute shape or goes against it, air pressurizes here, gets deadheaded, and has to get reaccelerated back out. So if I put the elbow on this way, notice the performance is decreased when you look at the Magnehelic gauge. Now if I take that same 90-degree elbow, turn it 180 degrees, and now the outside follows the volute shape, you notice that there's very little change in performance when we look at the Magnehelic gauge. Then we can put our straight run of ductwork here. It'll allow the velocity profile to even out, and we can get our static pressure regained. with very little loss. Thank you very much for watching. Hopefully all these configurations that we use to configure inlet and outlet ductwork helped answer your questions as to how ductwork changes fans' operating performance. If you have any questions, feel free to contact us at AMCA, the Air Movement and Control Association.
So any questions regarding 90-degree elbows at the fan discharge? Okay, moving on to our closing parts of our presentation. So, not paying attention, did not forward to, okay. Let's talk a little bit of some fonts of information on fans. Oh, there they come up. Okay. When you're moving 26,000 CFM through a fan, you're functionally moving 1 ton of air through the fan every single minute. So every 3 minutes, you're practically moving a pickup truck through that fan. Another way to look at it is that each pound of air or each cubic foot of air at standard conditions weighs 0.075 pounds per cubic foot. Sometimes I think that putting that extra decimal in there kind of makes it unrelatable. But if you think about it, you need about 13.1 cubic feet to generate 1 pound of air. And most mid-sized cars have a trunk that's around 13 cubic feet. So when you're driving your car around, if you have a mid-sized car, you're functionally driving around with 1 pound of air in the trunk at any given time. At 4,000 feet per minute, the air is moving about 45 miles per hour. So if you think about that pickup truck with that going through a piece of ductwork every 3 minutes, the straighter the ductwork is, the more efficient it's going to be. If you have abrupt T's, you have very tight radius elbows, it's like driving a car or a truck down a tight, twisty road. You're not going to get there as efficiently as if you have a nice straight road. And I think the reason why you see a lot of system effects is that people just think air being 0.075 pounds is super light, so they're not moving much mass. The reality is that you're moving a lot of mass through a fan at a relatively high speed, and you have a lot of losses associated with it. An inch of water gauge is a relatively small unit of measurement. You need about 27.7 inches of water gauge to equal 1 psi. As a result, you need about 900 inches to 1,000 inches of water gauge to fill up or pressurize a car tire. And the last one is that if you're running a fan 24/7 or any device 24/7, depending on what your utility rates are, it's going to cost you about $600 a year to consume 1 brake horsepower that's constantly running. So anything that you can save, if you can save 10 horsepower on a system, you're going to save $6,000 a year running that fan or any device on that system. Pretty significant savings. And that should also show up in that if you can sell something that's more efficient to an end user, yes, I understand that everybody's looking at initial first cost to purchase everything, but if you can sit there and show that, hey, your device might have a payback in 2 years, and every year after that, there's going to be a significant savings, that might be a key good selling point. Poll question. Bill Howarth, can the fan rotation discharge position be changed to avoid system effects? That's a really good question. And fan rotation and discharge position on certain fans can be altered. Sometimes it cannot. And it really depends on how the fan was originally constructed. Oftentimes, a lot of fan manufacturers with their smaller units have what we call rotatable fans that the housing, all the components bolt together, and you can sit there and change those configurations if, like, so for example, the original design for the piece of equipment changed prior to installation, or you're trying to reuse it in a different purpose. However, oftentimes larger fans or custom fans, they're not bolted together, or they're all welded together. And it's much, much more difficult to change the configuration of the unit uh, once it's been fabricated. Does that answer your question, Bill? If it doesn't, then just post something else up there and we'll get to that. Lisa, how do
Poll
we want to
question.
hold?
So
Pardon?
here comes the poll question.
Okay. Which of the demonstrated systems is one of true system effect and not a fan system effect? So basically, which one affects the system curve and does not affect the fan curve? And Lisa, do we want to just give everybody a
Yeah,
minute?
well, yeah.
Okay. And how do they click on that? They
Um,
scroll down and then,
it is showing up on their screen, and they get to select which of the answers they think is correct. And there is only one correct answer.
okay.
So we have 5 people who have voted so far. And there may be some people that don't want to vote, which is fine.
They don't
We'll
get a
give it.
cool grab bag
I
afterwards.
know. Depending on how many people get it right, Dave and I are going to have to dig deep in the prize closet.
The treasure trove of cool things. But it'd be fun.
It will be fun. So we'll give everybody about 30 more seconds here.
Are you going to count down, Lisa, backwards from 30?
No, because
No.
that would be monotonous, but I'll let you know we have about 10 seconds. So this is last call for votes. Get your vote in now. And then we'll close the poll and look at the results live on screen. So Dave, you want to do the honors?
Well, you have control of the screen, so go for it. And I'll explain it afterwards.
Well, the answer is, I have to be able to share my screen. So much technology adventure here. There's
So I
the
pop it up on
answer.
my screen.
There's the answer. Hopefully you all can see the slide.
Sorry, you can't see the slide.
Oh, I'm so sorry. It would probably help if I was sharing the proper screen.
There it is. Straight run of inlet duct. How many people got that right? Do you know?
I believe 5.
5 people. Okay. Can I take control of the screen?
You certainly can. All yours.
Okay.
Yes, we had 5 people get that right. 1 person guessed corkscrew elbow.
Mhm.
1 person guessed straight duct with corkscrew. And 3 people thought it might be either the straight discharge ductwork or the discharge elbows.
And all those were kind of good. I shouldn't say kind of good. All of them were legitimate potential responses, answers. And what we have to kind of remember is that, fortunately, this is all combined slides. So I'll kind of explain. The solid curve is the fan curve. The solid red curve is a system curve. So when you put on a straight run duct on the fan, and if you put a bell mouth on it, or take the bell mouth off, you put a hood, you put a flange on it, you put a damper on it, and you change it. You're not changing how the air enters the fan. It still enters the fan uniformly, still discharges the fan in the same method. So basically, you're shifting the system curve either left. If, for example, if you take the bell mouth off, it becomes more restrictive shift it left, put a bad hood on there, shifts it left. You close a damper on that, it shifts it left. So that's a system effect curve. If you put a corkscrew on the fan, it's going to change the entire shape of the fan curve and change it to something that might look like this dotted curve here. It's going to make it steeper, just like if you're closing a vortex damper off, it makes the fan curve steeper. Or if you take the don't have a full length of ductwork on the fan, you're not allowing for the velocity profile to even out, and so consequently you have a velocity pressure loss. And that becomes more significant as the fan gets wide open, less significant as you get close to peak here. So you're changing the fan curve shape with all those other devices because they don't affect the system, but they affect how the air either enters the fan or leaves the fan. Hopefully that makes sense. And congratulations to all those who succeeded. Hopefully they weren't AMCA consultants. They got the answer right.
Hopefully not indeed. And for anybody, for the 5
But
people.
even then, I would still recommend that they get it because I've asked a lot of people that have been in the fan industry for a long time, and it's surprising that how many people get it wrong.
Well, and
So-
for the 5 people who got the answer right, Dave and I will regroup. We'll get those gift items together and we will send them to each of you. From the reports that I can gather after this broadcast, I will have the names of all 5 people. So we will follow up with you through email and let you know what the next steps are.
And then did you want to go through the resource page and then
Yeah.
close out with final thoughts of?
Yeah, certainly. If anybody has any remaining questions for Dave, please go ahead and put those in the Q&A box while we just run through these last 2 or 3 slides. These are resources that Dave referenced during his presentation. ANSI AMCA Standard 210, which is also done in conjunction with ASHRAE 51-16. That is available for purchase on the AMCA store site. AMCA Pub 211-13 is currently available. It's a free PDF download. So if you go either to this web address or just go to the AMCA website and look up publications and standards, you can access that download. And we also online have a system effect video. It is not the same videos you just watched. It's about a 2.5 to 3 minute video that outlines the basic concepts of system effect. And as we had mentioned earlier, the PDF of this slide presentation and the video will be available on the Odell website within 48 hours. So you will have access to those materials and can use and or download or view those again. And for PDH credits, I will let you know that those will be issued within 30 days. People who are interested are going to get an email in approximately 1 hour that thanks you for attending and also includes the link for the survey that you need to take. If you've been on previous Odell broadcasts, you know that that's how we've been doing it for the past 6 weeks or so. So do we have any final questions out there for Dave about anything that was presented today?
Looks like we're good.
All right. Well, Dave, I certainly want to thank you for a fabulous presentation as always. It's pretty interesting that I, as a non-scientific, non-engineering person, watch these and get pretty excited about, wow, that's cool. So thank you for your time, as always. And thank you to Odell and the audience for their time and participation. And I also want to let people know, and we'll send you a reminder. Our next presentation is on Thursday, December 9th. It is 10 to 11 a.m. Eastern Time, so we're going back to the normal schedule. The topic will be stall detection and control in commercial and industrial fans, and that will be presented by Dr. Jeff Sheard,